Alright, so I got a request for a video about 6.10 Part B, and there's another problem in Chapter 6 that's similar, and they're both about finding the sample size necessary in order to find confident intervals of a particular degree of accuracy. And so this is reminiscent of the walrus problem from Chapter 4, where we wanted to, there's a margin of error for pounds that we wanted to find and we degree of accuracy that we were expecting or confidence level, and we were looking for how many walruses you needed to weigh in order to achieve both the confidence and accuracy. And so we have a similar question for uh, we have a similar sort of issue for proportion problems, and the way we think about that is much the same way. So let's recall that the standard error for proportion interval is definitely just the square root. Let me just make sure that that's all the way clear. So if we have a estimator for the proportion of a population uh, that satisfies some criteria, then the standard error is just that proportion times 1 minus the proportion over the size of the sample. And then we recall the margin of error is the standard error times the z-score, where this is given by the confidence level. All right. And so this is very similar to our setup that we used to have. So if you, I'm just going to write here, just recall from chapter 4, when we weren't dealing with proportion variables, we were just dealing with numerical variables, the margin of error was sigma over square root n z, right? That was what the margin of error was for uh, numerical variables in chapter 4. And so, as usual, we want to find an expression for n, and so we could set this up in the same way. If I square both sides, then on the left I get the margin of error squared is the square root dies and my z is squared. And then doing some algebra here, I can multiply n to both sides, and then I can both divide both sides by the margin of error squared. And so there you have it. That is a catch-all formula for how we could go about finding the size of the sample if necessary. So let's go take a look at an example problem and see how this would be applied. So we have um, 250 college students and want to know what proportion of college students smoke. So out of the random sample of 250 students from this university, 33 smoke. And we want to find a margin of error no larger than 1% at a 94% confidence level. And so, according to what we just wrote, the number of students would be 33 out of 250 times 1 minus 33 out of 250 times the z-score squared, where the z is determined by 94% confidence, over 0.01 squared, the margin of error squared. So, something that's really neat about Desmos 2 is that it will handle algebraic expressions just as well as arithmetic ones. So, n equals p times 1 minus p z squared, all of which over, let's call it error squared. And so we can set up a general formula like this if we felt like it. And now we just need to put in p and e and z. So the estimated proportion of people who smoke is 33 out of 250. So that's going to be our estimator for the proportions. That gives us our p-value, 33 out of 250. For z, we'll get that in a second. The margin of error is 1%, right? Because that's what's stated and given to us as the margin of error. What it needs to be is at most 1%. So that gives us P and E. As for Z, it's the Z-score associated with 94% confidence. And the Z-score associated with 94% confidence is the score I get if I start from the middle and I go out on both sides enough so that I capture 94%, right, off the data here. So it looks like 1.88079336. So let's go back here and go 1.8807936. And there we have it. We have an N of 4052.993, and so that translates to 4,053 students that needs to be sampled. Now, something that's very, very important to note is that even if this weren't a 0.99, even if this were a 0.01, we would still round that up, right? Because what this is telling us is that n needs to be this value in order to have 1% error at this level of confidence. If your n is less than that value at all, there will be more error. So if you round down, you increase the error. And so you always round up no matter what in these cases in order to get the right n. That will give you the right amount of error at the confidence level requested. So hopefully this was helpful. If you don't want to do all of this, we could have done all of this by hand, right? So if you didn't want to set up a general expression, we could have said 33 out of 250, that's P, 1 minus P, 33 out of 250, times z squared divided by 0.01 squared. But that gave us the same expression either way, right? So again, I hope this helps. And as usual, please feel free to ask questions and request other videos and contact me through Dfinity if you have any questions on anything else.